how'd you guys feel about it in general? What? Yeah, right. Well, that'll happen sometimes.
Usually I feel tired because it's the end of the day.
Okay. Well, I guess let's just set that aside, and after I grade them, maybe we can talk about it some more. Um, Really, there are just a couple of points I really wanted to get at with that. You know, make sure that you understood well enough to generalize to 3 dimensions. And in retrospect, I could have done that with a problem with less members, but you live and learn, you know. So, but I think there's some important stuff in there. It's just there's that same important stuff in easier problems. So today in class, I want to just uh, sort of this material we've been doing, I want to kind of let it breathe a little bit, go back, combine some elements that we've talked about. And so I want you to work on it's a structure. You're going to solve the structure and then use that solution to calculate the internal loads on the members. And we'll sort of do it in pieces. So I'll say what the first thing is to do, and then you'll do it. Then we'll come back and work on it together. Um, but here's what the problem looks like. Oh, and by the way, we have the second exam coming up soon. Next week? Yeah, a week from today. Okay, yeah, I think that sounds right to me too. Um, so, all right, so I'm going to have to think about it and let you know what topics are going to be on there. I suppose probably structures and internal loads. But let me think about that and I'll put it on D2L. Okay, so the structure looks like this. Um, a 10,000 Newton load is applied up, and this angle is 45 degrees. These are all pin joints. This length is 1 meter, and this pin is at the midpoint. And this height is 1 meter, and this pin is at the midpoint of that. All the things that look like midpoints are midpoints. And let's neglect the weight of each of these members. And after we're done, I'll just briefly mention how we would deal with the weights. And just so that we're all on the same page, let's put the coordinate system here, the origin here, and orient it that way. And let's number 1, 2, 3, and then A, B, C, D. The top one is E. Okay. And what we want to calculate is where on this whole structure is the greatest tension, shear force, and bending moment. So the way we have to go about this is, like I said, we have to solve this structure, figure out the external loads on each member, and then we have to go to those individual members and do the internal load calculations. And on each member, find where the maximum tension, shear force, and bending moment is. And then once you've done all three, you can see where the greatest is overall for those. So the first part of this problem is solving this structure. Anybody have any questions before we start with that? Okay, well, let's just do that. You've been doing structures for a while, so why don't you just work together and do that whole thing? I'm not going to break it up into pieces or anything. And then we'll come back and do the internal loads sort of together.